Okay, so welcome back. So finally, our big application of the residue theorem to um, something of interest coming from the world of real analysis, which is evaluating certain improper integrals of real valued functions. And so last time we had defined the Cauchy principal value. So for an improper integral that looks like this, for instance, the Cauchy principal value was this simplified limit, right? So this is not the usual. Way that this is defined. The usual way that this is defined involving limits is the following, right? So this improper integral is defined as the sum of these two limits, and this thing is said to converge if both of these limits existed, and so it converges then to the sum of those two limits, whatever they are. Okay. But if we are considering this thing, well, on one hand, this simplifies what's going on by combining those two limits into one limit, but it misses out on some things, right? So, for instance, I can't say that just because this limit exists that this thing converges. Okay, so in the other direction, so if this thing converges, then this Cauchy principal value that I've defined here um, actually exists, and it's equal to the value that, to which this thing converges. But if all I know is that this Cauchy principal value exists, it doesn't tell me that this underlying improper integral converges. And so I did an example of that yesterday. So my Cauchy principal value, for instance, of this thing is 0. But if I actually try to compute this improper integral from the original definition, I get two limits that don't exist, and so I'm stuck. Okay. But what we do then is we restrict our attention to integrands that are of a certain type. So for instance, what if we had an even integrand, right? So even means symmetric with respect to the y-axis, so f of minus x is equal to f of x for all of x. Then, in this case, if I know that this Cauchy principal value exists, then its improper integral, which is, this, the integral from minus infinity to infinity of f of x, is equal to the Cauchy principal value in this case. Okay. And so why this occurs? Well, this makes important use of this symmetry that you get from f being even, right? And this is exactly what happens. So as you take the limit, these two things go to infinity. This left-hand side becomes the this improper integral. This right-hand side goes to the Cauchy principal value. And of course, it's not. This doesn't just work for when you have, a double improper integral like this, so that both endpoints are minus infinity and infinity. This also works for an improper integral of the form, it's the integral from 0 to infinity of f of x dx. This is 1/2 the Cauchy principal value. Again, f needs to be even here. Okay. Okay. And so this is not going to be a general method. We're going to have to make some assumptions here on what sorts of integrands we're looking at. But assuming that we have an even function that we're dealing with, then we can make this work. Okay, so how do we make this work? What is the idea? Okay, so idea. I restrict my attention to integrands of the form f of x is equal to p of x over q of x, which are going to be rational functions, meaning p and q are polynomials. Okay, where p and q are polynomials with real coefficients and no factors in common. Okay, so if they had any factors in common, I've already gotten rid of those, and so what I'm left with is P of x over Q of x. Okay, also assume that Q of z, now thinking of this polynomial as a function of a complex variable, assume that Q of z has no real zeros and has at least one zero above the x-axis. Okay. All right, so if that's the case, it has at least 1 0 above the x-axis. We're looking at this rational function p over q. Okay, so then what is next step? So step 1, identify the distinct zeros of this denominator. Okay, so identify distinct zeros of Q of z that lie above the x-axis. So by this assumption that I've underlined up here, there's at least one of these. So identify distinct zeros of Q of z that lie above the x-axis. That's the first thing that I do. Okay. So there's finitely many of those, okay, at most. So label them z sub 1, z sub 2, all the way up to z sub n. Okay. Of course, how big is n? Well, n can't be more than the degree of q, right, by the fundamental theorem of algebra. Okay, then step 2, integrate f of z, which is p of z over q of z. Okay. Around a particular curve enclosing those zeros. So to see what this curve looks like, let's say that our picture is something like this. So here's my x-axis, here's my y-axis. Okay. This function q of z has no zeros on the x-axis. It has some number of zeros above it, however. So maybe they look like this. So here's z sub 1, here's z sub 2, and maybe here's z sub 3. There's some number of these. These are all zeros of q of z. Okay. And I choose r greater than 0 big enough. And what do I mean by big enough? I choose r greater than 0 big enough so that if I draw the curve along the x-axis from minus r to r, oriented, like I said, from minus r to r, and then take the semicircular piece with this as its diameter, so we'll call that piece c sub r, and it's oriented in this way. Well, now we have a contour that is positively oriented that encloses all of these z sub i's. The idea here is I specifically choose an r that's large enough to make this happen. Okay. right. So this C sub r is the top half of the circle of radius r. Okay, taken counterclockwise. All right. And so, what do I do here? Well, the idea is that if I'm integrating over this closed contour, right, whatever I'm calling that, then I could split that into an integral along this one and along this piece. Okay. And since that's a closed contour and I'm integrating some function that has, say, some singularity, some isolated singularities here, I can use the residue theorem to actually tell me what that thing is going to be. So what is the integral along this contour that I'm tracing out with my finger? Well, another way of writing it is that the integral from minus r to r of f of x dx plus the integral. So the reason I can say this is f of x dx is because along the x-axis, right, this is a real valued function. Okay. And so I add to that the integral along this piece of f of z dz. Okay. So this is my integral along this entire contour that encloses these singular points. But by Cauchy's residue theorem, that should be equal to 2 pi I times the sum of the residues at those points. So this is the sum from k equals 1 to n of the residues at z is equal to z sub k of f of z. And this is exactly what I want. Okay. All right. And so, if I subtract from both sides here, so my integral from minus r to r of f of x dx can be thought of as 2 pi I times the sum of those residues. This is z sub k. F of z minus this integral over this semicircular piece of f of z dz. Okay. And the idea here is if I can show that this limit goes to 0 as r goes to infinity, then I'm in business, right? So if this thing, goes to 0 as r goes to infinity, then what have we shown? If this term goes to 0 as I let r go to infinity, I take the limit as r goes to infinity of this thing. This is my Cauchy principal value, right? So this is my Cauchy principal value. So what this means is that my Cauchy principal value, the integral from minus infinity to infinity of f of x dx, is equal to 2 pi I times the sum of these residues at those zeros indicated above. Okay. Restating this, when we're happy, and this actually allows us to compute the improper integral itself and not just the Cauchy principal value. And thus, if f is even, what this means is that the integral from minus infinity to infinity of f of x dx can be computed in this way as 2 pi I times the sum of the residues of f, or the integral from 0 to infinity of f of x dx is half of that, so it's pi I times the sum from k equals 1 to n of the sum of the residues. Sorry. All right. And this is the method that we're going to use to compute these improper integrals. Now, this is one way we're going to do it. I'm going to show a slight modification of this when we have integrals of a certain form that can show up in Fourier analysis. But this is how we're going to do it. Okay. Okay. And so, to actually see how this works, let's do an example. So, let's evaluate the integral from 0 to infinity of x squared over x to the 6 plus 1 dx. Okay. So notice, I could sit you down on, this is, if I sit you down in Calc 2 and ask you to do something like this, notice that, right, this is something that there's no mention of complex numbers anywhere. This is just an improper integral you're trying to compute. Okay. What's cool about this is that this is going to take us through literally all of the material that we did. Okay, we are going to use everything that we've learned so far. We are going to use everything learned so far. In this course to evaluate this thing. So this touches on everything from like the first day of class to now, to the last sheet I just took away. Okay, so how does this work, first of all? So first, I look at this integrand function, and rather than thinking of it as a real valued thing, I think of its complex counterpart, right? So this is z squared over z to the 6 plus 1. So if I'm looking at this thing here, this has isolated singularities at the zeros of the denominator. Right, so this has isolated singularities at the zeros of z to the 6 plus 1. So z to the 6 plus 1 is our q of z, okay, from the previous setup. What are the zeros of z to the 6 minus 1? Well, z to the 6 plus 1. If z to the 6 plus 1 is equal to 0, right, this is z to the 6 is minus 1. So this is really just sixth roots of minus 1. Right, so z is equal to the set of 6 roots of minus 1. Right, so it's minus 1 to the 1/6. But what is this? Right? So these are the 6th roots of minus 1. Right? By the fundamental theorem of algebra here, there are 6 of these things. Okay? And they are spread, equidistant around unit circle. Okay? And so, how do I describe these? So my 6th roots of minus 1, how can I list those? Well, using what I did on like the second day of class, right? My 6 roots of minus 1 are described as e to the I times pi over 6 plus 2k pi over 6, right? Where k goes from 0 to 5. Right, those are my 6th roots of minus 1. This is how to find roots of a complex number. Okay. Now, none of those lie on the x-axis, right? So none of these are real. All of these are purely imaginary. Okay. So, or I should say, these are, none of these have 0 imaginary part, right? No, they're not necessarily purely imaginary, but the idea here is that none of them lie on the x-axis, so I'm good there. That was one of the requirements I had. Does at least one of these lie above the x-axis? Yeah, actually 3 of them lie above and 3 lie below. Right, so 3 of them lie above, so in fact c sub 0, which is e to the I times pi over 6, right, c sub 1, so in this, when I have c sub 1, this is I to the pi over 2, so this is I, right, e to the I pi over 2, that's I, and c sub 2 is e to the I 5 pi over 6. So these 3 lie above the x-axis. That's what I need. The rest lie below. I don't care about those. Okay, I only care about these. Okay. All right. Now, these 6th roots of minus 1 are equidistant around a unit circle, so I only need to choose my radius here to be bigger than 1. So choose r to be bigger than 1. Okay. So then what situation am I looking at here? Well, drawing this picture again. Situation I'm looking at is I have points that look like this. So here's C naught, here's C sub 1, here's C sub 2. Okay, there's my points that are singularities for f of z. And I have a curve defined by, if I choose r to be bigger than 1, then this curve described in the same way as before. So here I orient it like this. I have this upper half of the circle of radius r centered at the origin. Again, oriented in this way. And so all of those singularities of f lie inside of this thing. Okay, and so by this fact that I listed here, when I'm in this situation, I can think of integrating over this whole contour. This is closed, and it's a semi-closed contour around the points where f has isolated singularity. So by the residue theorem, I can compute that contour integral as 2 pi I times the sum of the residues. Okay. Well, how does that work here? Well, then this becomes the integral from minus r to r of f of x dx. But remember, f of x is x squared over x to the 6 plus 1, right? Plus the integral over the semicircular part, f of z dz, and that is equal to 2 pi I times the sum of the residues at these 3 points, which I will label as B0 plus B1 plus B2. So that's the sum of those residues. Okay. All right. Now, by a theorem from the last 2 lectures, each C sub I is a simple pole of F. And if I want to compute these residues, B sub k, so this is the residue at Z sub k, or C sub k here, the way that I've written it, so maybe I'll write these as C sub k. Okay, C sub k of f of z, which is z squared, over z to the 6 plus 1. Okay. How do I compute this? Well, this is, let me find my sheet showing the exact theorem that I'm using. So I've got it somewhere here. Here we go. If P and Q are analytic at a point, P is not 0, Q is 0, Q prime is non-zero, then this ratio, P of z over Q of z, has a simple pole at z0. And to compute a residue, this is just P of z0 over Q prime of z0. That is true for this thing, right? So at each of these c's, z squared is non-zero. But at each of these c's, z to the 6 plus 1 is 0, right? Each of these are solutions of that because they're 6th roots of minus 1. But if I take the derivative of this, that's 6 times z to the 5th. 6 times z to the 5th is non-zero for each of those c. And so using that theorem to compute this residue, all I have to do is find the derivative of the denominator here and plug in the point I'm finding the residue at into P over Q prime. Okay, and so this is C sub k squared over 6 C sub k to the 5th. Or this is 1 over 6 C sub k cubed. Okay. So what is this? Let's compute each of these. So what's B sub 0? Right? According to this. Well, remember, C sub 0 is e to the I pi over 6. So B sub 0 here is 1 over 6 times e to the I pi over 6 cubed. But this is e to the I 3 pi over 6 or e to the I pi over 2. That's I. So this is actually 1 over 6i. That's my residue at C sub 0. What about C sub 1? So my residue at C sub 1 is 1 over 6i cubed. I cubed is just minus I, so this is minus 1 over 6i. And lastly, the residue at C sub 2, this is 1 over 6 times e to the I 5 pi over 6 cubed. Okay, so what is that? So this is e to the I 15 pi over 6. Okay, so that's e to the I 3 pi over 6 because e to the 2 pi I is 1. So what's left over is e to the I3 pi over 6, which is e to the I pi over 2, which is I. So this is actually 1 over 6i again. Okay. All right. And so, how does this help me? Well, now this means that using this fact, I can see that thus the integral from minus r to r of f of x dx plus the integral over the semicircular part, c sub r, of f of z dz is equal to 2 pi I times the sum of those residues, but those residues were 1 over 6i minus 1 over 6i plus 1 over 6i. Okay, so these two cancel. I have 1 over 6i here. It cancels with the I, so this is pi over 3. And so written another way, the integral from minus r to r of f of x dx is equal to pi over 3 minus this integral over the upper semicircular part of f of z dz. Okay. So next, we show that this limit as r goes to infinity of the integral over the c sub r of f of z dz is equal to 0. Now, in the past, in the course, you actually had to do this a couple of times. What did you do in order to get this done? Idea, right, we find a suitable bound. So we find a suitable upper bound on the modulus of this integral. Aha, so now you're understanding why when I said that we use everything that we've learned up till now, I really meant it, because we're even using this this upper bound business, right? Finding an upper bound on an integral like this, okay, which we did all the way back in chapter 4, like a couple weeks ago. All right. Okay. So how do we do this? So recall, C sub r is actually the upper part of the circle on which the modulus of z is equal to r, right? Okay. And so, for instance, the modulus of z squared, we know that that is the modulus of z all squared, which is r squared, right? And the modulus of z to the 6 plus 1, by our favorite inequality, is greater than or equal to the absolute value of the modulus of z to the 6 minus 1, which is, of course, r to the 6 minus 1. And so, on that curve, C sub r, the modulus of f of z is equal to the modulus of z squared over the modulus of z to the 6 plus 1, which is less than or equal to r squared over r to the 6 minus 1, just directly from those inequalities. So, if I define this thing to be my m sub r upper bound constant, this means that the modulus of that integral over c sub r of f of z dz is bounded above by this m sub r times pi r. Right? Where did I get pi r here? So this, maybe I'll circle it here. This is length of that semicircular part, c sub r. This is the theorem that says that if you have a bound on the modulus of your integrand, then at most the contour integral along that piece, right, is that bound m times the length of the contour L. Okay, so this is m times L, where m is the bound I found up here from those inequalities, and pi r is the length of that semicircular piece. Okay, but of course m sub r times pi r, that is just this thing. So this is the integral over c sub r of f of z dz. This is less than or equal to pi times r cubed here over r to the 6 minus 1. Okay. Let's take the limit. All right, so take the limit. So the limit as r goes to infinity of this thing is what? Well, what is the limit as r goes to infinity? What does this thing go to? So as r goes to infinity, this thing is a degree 3 thing over a degree 6 thing. Okay. And so, since it's a degree 6 thing over, or sorry, a degree 3 thing over a degree 6 thing, as r goes to infinity, this goes to 0. And so this limit is 0. And we're done. Okay. So we have shown that the limit as r goes to infinity of this contour integral is 0. And we're very, very close to finally getting what we want. Thus, combining all of this, our limit as r goes to infinity of the integral from minus r to r of f of x dx, this is our function in question. This is equal to pi over 3 because this bit, so if I go back here and I take the limit as r goes to infinity, on the left hand side I have that limit, and on the right hand side, since this is going to 0, I have pi over 3. Okay, i.e. the Cauchy principal value of the integral from minus infinity to infinity of f of x is x squared over x to the 6 plus 1 dx is equal to pi over 3. But this is even. Okay. But x squared over x to the 6 plus 1 is even. And so the original thing that I wanted to compute, the integral from 0 to infinity of x squared over x to the 6 plus 1 dx, is equal to pi over 3 over 2, so pi over 6. So, going back, let's kind of try to trace through what it is we did exactly. If you think about it, all right, I slide that problem in front of you. All right, so I slide this problem in front of you. The integral from 0 to infinity of x squared over x to the 6 plus 1 dx. Let's say evaluate that. Okay, let's say you have no idea how to do it. You've never even heard of a complex number before. Okay, well, if I, using all these techniques, then say, oh, well, the answer is pi over 6 because I used all these techniques. And you're like, well, I don't believe in complex numbers, right? How did you get that? I don't believe any of this worked. How do I check this? If you thought of like numerically evaluating this integral, and you'd see, oh, wait, this is pi over 6. That's exactly what the value of this thing is. How did you figure that out? Well, you passed into the world of complex analysis to answer this question coming to you from real analysis. And so this is just a single instance of when seemingly maybe doing something that's a little more esoteric, seemingly doing something that's maybe not exactly related to the original thing you were asked, actually is the thing that lets you answer what it is that's going on, right? You dipped into a realm that maybe you thought didn't have anything to do with what was going on, and it actually allowed you to compute this thing. Okay. All right, so I have one more example. I have one more example real quick, and that is a Fourier type integral. Okay, so one more example. This will be our last example of the class. And this example comes to us from Fourier analysis. Okay, so this is improper integrals from Fourier analysis. Okay, and so the types of integrals that we will be discussing will look like this instead. Or maybe something like this. Okay, so these arise in Fourier analysis. Okay, so A is some positive real number, okay, in both cases. Okay, we're still going to assume that f of x is p of x over q of x as before. So all the assumptions carry through. Okay, no factors in common. Q of x has no zeros on the real axis and at least one zero above it. And so the idea here is to try to modify what it is I did before. So I can't exactly do what I did before here because if you notice, right, so recall that the modulus of sine of az squared is sine squared of ax plus sinh squared of ay if z is x plus iy. And the modulus of cosine a of z squared is cosine squared a of x, or a times x plus sinh squared ay. So actually both of these things are unbounded, right? This is the thing that we had even before Liouville's theorem, okay, that told us that these things were behaving differently, but these things are actually unbounded. Okay. So what does that mean? What is it that I do kind of instead here? How do I deal with this? The idea then, so if I remember that sinh of ay is e to the ay minus e to the minus ay over 2. Okay. The idea is that this integral of from minus r to r of f of x e to the I ax dx is the thing that I'm doing here to transform my, so this is involved with the thing called the Fourier transform, if you've seen this before. But if I ignore that for a second and just say, if I consider something like this, right? Well, this is, if I look at the real and imaginary part, the real part is the integral from minus r to r of f of x cosine of ax dx plus I times the integral from minus r to r of f of x sine of ax dx. So I cannot directly look at these integrals and things involving them and slap modulus signs here and talk about what it is I'm doing here, because these things are unbounded. So what is the argument that I use? Well, while I can't argue from this, I can use the fact that this thing, okay, actually is bounded. So how does this work? Okay, well, so first of all, if I look at the modulus of e to the iaz, right, this is the modulus of e to the ia x plus iy, right, which is the modulus of e to the minus a y times e to the iax. But then this is just e to the minus a y, and this is bounded in the upper half plane. Okay. All right. So actually, we're fine here doing all of this. Okay. Okay. All right. And so we're going to be fine, but we have to modify the way that we did our example just slightly. Just slightly. So let's see how this works. Let's do our one example here. As I said, this is our last example of the course. So I want to compute the integral from minus infinity to infinity of cosine of 3x over x squared plus 1 squared dx. Okay. So this integrand is even because cosine is even and because I have an x squared and I'm squaring it here, but this thing is even, so that integrand is even. So all I need to do is find the Cauchy principal value and I'm happy. Okay. All right. And so we view this, right, as the integral from minus infinity to infinity of f of x cosine of 3x dx in our example, where f of z is this function 1 over z squared plus 1 squared, right? Okay, notice if I'm going to be using this fact ultimately, okay, and then looking at the real part, that's the idea. So notice that f of z times e to the I3z, okay, is analytic everywhere on and above the real axis except at a single point, which is a singularity, which is I here, right? So this is analytic everywhere on and above the real axis except at z equals I. Okay, which I can put in a semicircular region as in the previous case, right? All I have to do is pick r bigger than 1 here. Okay, and so what does my picture look like? Here is I, and my picture looks like this. Okay, so my upper semicircular part C sub r, here's minus r, here's r. Okay, so this is what's going on. And so, using the exact same formulation as before, the integral from minus r to r of e to the I times 3x over x squared plus 1 squared dx. Okay, this can be written as 2 pi I times the residue at I of f of z e to the I3z minus the integral over the semicircular part of f of z e to the I3z dz. Okay. Now, what is the idea here? Now, notice that f of z times e to the I3z can be written as the following. This is phi of z over z minus I squared, where phi of z is e to the I3z over z plus I squared. So I've fully factored that polynomial in the bottom. And so, and thus, z equals I is a pole of order m is equal to 2 for this f of z e to the I3z. Thus, this residue at z equals I of f of z e to the I3z can be computed as the derivative of phi at I. Okay, well here's phi. If I go ahead and take this derivative and compute it at I, so I'm not going to do that, but you can check that this is the case. What I get is 1 over I e cubed. Okay. And so what I want to do, I want to take this equation here and equate the real parts. So I want to take the real part of this thing. Okay, so equating the real parts of star here, we'll call it. And because this residue I've computed is 1 over I e cubed, equating the real parts. So this is the only real trick, right? I deal with a slightly different integral and then I equate the real parts and I'm good to go. So equating the real parts, what I get is that the integral from minus r to r of cosine of 3x over x squared plus 1 squared dx is 2 pi I times 1 over I e cubed, so that's 2 pi over e cubed, okay, minus the real part of this integral over the semicircular part of f of z e to the I3z dz. Okay. Note, when z is on the semicircular part, which of course is the upper half of the circle, modulus of z is equal to r, then the modulus of f of z is less than or equal to 1 over r squared minus 1 squared, which I can take to be my m sub r here. Okay, and notice that the modulus of e to the I3z is actually less than or equal to, well, it's less than or equal to 1. So it's actually equal to e to the minus 3y, which is less than or equal to 1. Okay, for a point like this. And thus, what is the bound on this thing? So if I look at the absolute value of the real part of this integral, e to the I3z dz. So if I look at the bound on this thing, so this is less than or equal to the bound on the modulus here of this thing. I always have that inequality, right? But this thing, using my theorem from before, is m sub r times pi r. Right? But as r goes to 0, this thing goes to 0 because m sub r is 1 over r squared minus 1 squared. So this is pi r times r squared minus 1 squared. So as r goes to infinity, this thing goes to 0. And so, taking the limit as r goes to infinity, because this thing is even, I get exactly the thing that I want. This thing goes to 0, and I'm left only with that term. Thus, the integral from minus infinity to infinity of cosine of 3x over x squared plus 1 squared dx is 2 pi over e cubed. Bet you wouldn't have guessed that one, right? Okay. And so I kind of view this as like the ultimate justification for everything that we did in this course because of how useful it is in kind of an unexpected way. Okay. And so that's that. I will post your final exam later today, and it will be due. It will say that it's due by like Sunday at midnight. That will be the hard deadline. It will be of a length that you could do it this evening. You could finish it this evening. If you sat down, it shouldn't take you longer than like an hour and a half or 2 hours. Okay. And then that's that. That's the end of the course. So let me know if you have any other questions. I'll be on email all over the weekend, so if you have any other questions, you can let me know. Other than that, I enjoyed teaching you, so hopefully you got something useful out of it. And I will hopefully see you around campus.